This week we're going to be looking at a number of common circuit structures, or structures that we frequently find within electrical circuits. My name is Lee Brinson, and I'm an electrical engineering instructor at Salt Lake Community College. We're first going to look at series resistance. We've already seen it last week, but we're going to look at it a little bit more specifically as series connected resistances. We'll talk about the equivalent resistance and look at a concept known as voltage division. We'll then look at another structure, which is a parallel combination of resistances. We'll show the equivalent resistance of two resistors connected in parallel, and then introduce a concept known as current division. We'll then look at variable resistors, how they work, and how you can hook them up to get variable amounts of resistance. We'll then look at a common structure known as a Wheatstone bridge, and finally we'll consider a circuit that involves both series and parallel circuits. The first two structures we'll look at will be the series connected resistance and then the parallel connected resistance. In series, we have defined the series connection as being, or say that two devices are connected in series if the current through each of the devices is the same. So in this case here we have a voltage source which will be driving a current that will come through R1 and R2 and then back. We know that they have the same current because there's no other place for the current to go. There's no branching that would allow current from the source to go in either one direction or the other. So R1 and R2 are said to be in series. We saw before that the equivalent resistance, or the total resistance seen across these two, or the resistance that this voltage source would see when the resistors are in series, is simply equal to the sum of the two resistances. So our total would be R1 plus R2. Now we know from Ohm's law that there will be, because there is a current flowing through each of these resistances, there will be a voltage drop across each of those two resistances, and the voltage drop will be proportional to each of these two resistors. So the larger the resistor, the larger the voltage drop across it. And in fact, it can be shown, we'll show it in some of the more advanced classes, we'll derive these formulas. The voltage across V1 will equal the total voltage, V sub S, times the ratio of R1 over R1 plus R2. This is a percentage, if you will, or a ratio of the value of R1 relative to the total resistance R1 and R2, R1 plus R2. Similarly, the voltage across V2 can be calculated by taking V sub S times R2 divided by R1 plus R2. So for example, let's say that V sub S is equal to 12 volts and R1 is equal to 3 kilo ohms and R2 is equal to 33 kilo ohms. We can then derive, or from this voltage divider formula, we can say then that V1, which is the voltage across R1, R1 of course is 3 kilo ohms and R2 is 33 kilo ohms, for a total of 36 kilo ohms. 3 plus 33 is equal to 36 kilo ohms. V1 then, the voltage across R1, across the 3 kilo ohm resistor, will be 12 times 3 kilo ohms divided by 3 plus 33 kilo ohms, which is equal, let's just go ahead and do the fraction here, 12 times 3 over 36, that's 1 over 12, or 1 volt. Notice this ratio of 1 to 12, or 1/12. R1, 3 kilo ohms, is 1/12, or 3/36 of the total resistance. So this is 1/12 of the total resistance. The voltage V1 then is 1/12 of the total voltage. Similarly, V2 will equal 12 times our total voltage dropped across the two resistors times 33 over 3 plus 33, which is equal to 12 times 11/12. Now, this ratio corresponds to the ratio of R2, which is 33K, to the total resistance of 36K, or 11/12 of 12 is 11 volts being dropped across this resistor. So V2 equals 11 volts, V1 equals 1 volt, and the total voltage, 1 plus 11 equals 12, which is the total voltage drop across the two resistors.